Okay, any questions? All right, so last time we started chapter 12, in which we are considering one of the peripheral devices that is integrated in the HCS12 microcontroller, which is the analog to digital converter. This is one out of several devices that are integrated within this powerful micro controller. And as we said right at the beginning, that this is the distinguishing feature of microcontrollers when compared to CPUs, general purpose CPUs or microprocessors, which is the integrated peripheral devices. Many of the functionalities, many of the operations that you might need in designing embedded systems, you can find them integrated inside the microcontroller itself, which is something that you don't find in general purpose microprocessors. So our first example on such peripheral devices is the analog to digital converter. So last time we discussed the basics of the A to D conversion process. And we said basically this process is very important, is required because our microcontroller is digital, while the physical quantities that we usually want our embedded system to work with are analog quantities. So there has to be some sort of transformation, conversion, in order to be able to deal with these quantities. And this process is the A to D process, which involves the three basic steps, as we said last time: the sampling, the quantization, and the encoding. Okay, so we talked about this, and we mentioned this important thing, which is the need for transducers or sensors in order to convert non-electrical physical quantities such as temperature, humidity, light into electrical quantities such as voltage. So this is done using transducers or sensors, and the output of such devices is the output, that is the value that, or the signal that is fed into the analog to digital converter. Then we talked in a little bit of details about the sampling process and the quantization process and the encoding process. And we talked about some of the features or characteristics of the A to D converters in general. So we talked about the reference voltages, or basically the voltages that define the range which our converter is capable to work with, which is the input range. It is called usually the input range. Also, we talked about an important feature of the A to D, which is the resolution, which is basically related to how many bits we are using to represent the samples that we are taking and the quantizing. And this basically, the number of bits determines the number of quantization level and determines the quantization error. How much error is introduced into the quantization process. The more bits that we have, the higher or the better the resolution and less the quantization error. And also we talked about how to do the conversion from the analog sample that we take through sampling and the quantization into digital representation, and the opposite. And this is basically the simple equation that we will use, assuming that our A to D is ratiometric. In other words, the input voltage is linearly proportional with the digital representation, or vice versa. So the relationship between digital representation and analog representation or analog value is basically linear. And we showed last time how did we come up with this simple formula. And here the range is basically the input range, which is the V reference high minus V reference low. And we talked about this very important thing, which is in order to get the best accuracy in the conversion process for some input signal, we need to match the reference voltages with the range of the input signal. This is an example. And also we talked about the conversion speed and the digital interface. And we stopped here, which is basically, we said we are going to discuss the components of the data acquisition system. Now, the A2D by itself is only responsible of converting the sample value into a digital representation. However, this is not the only thing that you might need in order to convert some physical quantity, to acquire some physical quantity and convert it into digital representation. You might need other components, and these components together, they form what we call the data acquisition system. So one of these components is basically what we talked about last time, which is the A to D converter itself, which has certain number of bits, which has certain reference voltages, and the analog input, which takes the sample value and converts it into the digital output. However, in order to do this, to obtain the digital representation of some physical quantity on the other end, we may need to use different elements, other elements. The very first thing that we might need to use is the transducer or the sensor in order to convert, let's say, the temperature into voltage or electrical representation in order to be appropriate or to have it suitable for the electronic device, which is the A to D. So the very first thing that we will need is basically a sensor or a transducer to convert from physical representation, non-electrical physical representation into electrical representation, such as voltage or current. Another component that we might need, and this is something we talked about last time also shortly, which is what we call preconditioning circuit or amplify and offset circuit. And this is basically an electronic circuit where you might need to pre-process the voltage or the electrical quantity that you get from the sensor in order to match it with the reference voltage of the A to D. So for example, we said, let's assume that the reference voltages are from 0 to 5 volt, while the input signal is from, let's say, 0 to 1 volt. So in this case, we are not utilizing the input range or the reference range of the A to D efficiently. We need to scale the input signal from 0, 1, which is from 0 to 1 to 0 to 5. And here comes the rule of this component or this element, the amplify and offset. You might need to scale the input voltage or the analog voltage up. You might need it to scale it down. For example, let's assume that you are reading the voltage of the power outlet in your home. The voltage is from minus, what is the voltage? From minus 220 to 220, right? Which is much higher than the reference voltage. So in this case, you need to scale it down. And also it is negative. So you need to push it up in order to make it all positive to match the fact that the input range of the A to D is unipolar in this case. So this is the rule of this circuit, the amplify, or this block, which is the amplify and offset, where you will need to use operational amplifier to design scaling circuits, to design level shifting or voltage translation circuits, as we will see in the following 2 slides. Another component that we might need to include is a filtering component or a filtering element, or basically a filter. We might need to filter the incoming signal, analog signal, before we feed it into the A to D. And what is the purpose of filtering the signal? Or what is filtering at the beginning? What do you mean by filtering? Anyone has an idea?
مش عارف يعني إذا بيكون في noise مثلا على السيجنال اللي داخله بيشيلها.
This is one application for filtering. But what do we mean by filtering? What is filtering?
بعرف في شيء اسمه مثلا هاي لو باس فلتر، هاي باس فلتر او شيء.
Exactly. Exactly. Like any signal that we have in the time domain, it has a frequency content. It can be decomposed into frequency components according to the Fourier series or Fourier transform. And the purpose of filtering is to suppress or to pass subsets of these frequencies. So if we let the low frequencies to pass through and we suppress the high frequencies, then we have a low pass filter, while the opposite is also true. If you allow the high frequencies to pass through and you block the low frequencies, you have a high pass filter and so on. Now, so this is filtering. Basically, you remove some of the frequency components and you keep others. What is the purpose of filtering in this case? As Yazan said, one purpose of filtering that you might need to in this acquisition system is to remove the noise. For example, you might know that your input signal has a frequency content that is from 0 to 1 kilohertz. So you want to make sure that only these frequencies come are passed to the A to D. So you may use a 1 kilohertz low pass filter to pass only these frequencies, assuming that the noise has a frequency higher than 1 kilohertz. So one purpose of using the filters in this system is to remove unwanted signal components such as noise or any other signal that is not part of my signal. This is the first thing why we might need a filter. Another thing, if you remember last time, we said that in order for the sampling process to be reversible, in other words, to be able to represent the signal, we need to have the sampling frequency to be greater than twice the maximum frequency content in the image. In other words, if we have the sampling frequency, the rate at which we are taking the samples specified and fixed, so the maximum frequency content that we may feed into the A to D, which is performing the conversion, should be less than Fs, or the sampling frequency divided by 2. So what if our signal has a frequency content that is greater than this value? If you remember from your signals course, this will result in a problem called aliasing. Okay, I don't want to go into the details of this, but in order to avoid problems, the aliasing problem, which will make the sampling process not reversible or not capable of representing the signal, we need to make sure that the frequency that is fed into the A to D matches this, assuming that we know the sampling frequency that we work with. So what we will do usually, in order to do that, we will pass. So this is the transducer, this is the amplify and offset. We may use, let's say, a low pass filter with a cutoff frequency FC equals Fs over 2. Or less than Fs over 2, which means what is Fc? It is the cutoff frequency. It is the frequency, it's like the threshold, which below which the signal is passed. Above this value, the frequency components of the signal are blocked. So the second reason for using this is to make the sampling theorem applicable, to make the sampling theorem work in our case, which is we need to band limit the input signal. We need to limit the frequency content of the signal to match the sampling frequency of the analog to digital converter. So you might need to use a low pass filter with a certain cutoff frequency that matches or that is proportional to the sampling frequency of the A to D. So this is the second component that you might put in your system in order to acquire the input analog signal. The third component that we might need is this, which is called the multiplexer, or specifically the analog multiplexer. And the idea here is very simple. We know the multiplexer, the idea of multiplexer from digital logic design, which is basically a circuit that has many inputs and one output, and you can select using another set of inputs, which data input is allowed to pass to the output. So the idea here is the same. We have a multiplexer, which is a device that has several data inputs, that has one data output, and has input select lines or selection inputs through which we can select which input to pass through. Why do we need such component in our system? Because usually this A to D is kind of expensive component, kind of. It is expensive to buy, it is expensive to operate, and so on. So imagine if you have a system, you are designing a system in which you have more than one signal to be sampled and converted into digital format. It is not efficient, it is not cost effective to have one A to D for each of these signals. Alternatively, the common practice is to have a single analog to digital converter and allow these signals to share this. In other words, this A to D is multiplexed or shared between multiple input signals. So you can take a sample for this, take this signal, sample it, convert it, then you move to this next one, then you move to the next one, then you move to the next one. So you are sharing the analog to digital converter. So this is a multiplexer, but we need to keep in mind it is an analog multiplexer. It's not a digital multiplexer. It can multiplex analog signals. You can't go online and order an IC that is called, for example, 74153. 153 is a multiplexer, but it is a digital multiplexer. It doesn't work in this case. You need to have an analog multiplexer, which is basically built using also op amps. Okay, but it is also available in the form of an IC. Okay, so these are three components. Of course, four components. You need the transducers, you need amplify and offset or precondition the circuit. You need some filtering. You might need some filtering in order to limit the bandwidth of the, to match the bandwidth of the input signal with the sampling frequency that you are using to collect the samples. And usually, you might need to have an analog multiplexer to allow the sharing of the A to D between multiple signal sources. So these are the first four elements. The fifth element is a very important component, which is called the sample and hold circuit. The sample and hold circuit. And this is essentially where the process of the A to D starts. This is essentially where the process of the A to D starts. We said that the A to D process is includes sampling, quantization, and encoding. So what did we do in sampling? Basically, we took samples from the input signal. So on the paper, it was like, when I did the drawing last time, it's just like I pick this one, pick with this sample, pick this sample, and so on. However, how to do this in practice? How to take a value, one value from the input signal. This is, let's assume, our sensor, and it is producing some signal that is changing like this. And now this is the A to D that is expecting to receive some input or analog input, which is basically one value that represents the sample. So how can I take a value from here and feed it into the A to D? If I connect them like this, then the A to D will always see the whole signal and how it can convert a time varying signal, a signal that is varying. If the A to D is assumed to convert, then I have to present to the A to D, I have to feed the A to D with one value that is fixed, that is not changing, and I need to keep this value fixed until I finish the conversion process and produce the digital output. So the question is how to take one sample from this. Basically, I don't want the A to D to see the signal all the time. So what should I do? What can I do? I can have a switch here, right? I can have a switch here. And if I want to see the input signal, I want the A to D to see the input signal, I just close this switch. And in this case, the voltage that I see here is the same as the voltage as I see here. However, I need to open the switch as soon as possible or in zero time in order to read 1 point only, right? So when I do this, I am sampling, but I need to open the switch very fast in order to hold the signal, in order to have one value here which represents this value. Okay, so this is also still very abstract. So in order to take one value, I close the switch and then I open it in zero time. So in this case, I assume that I have this value here. However, when I open the switch, is it true? Let's assume that this voltage is 3 volt. Will I have a 3 volt here after I open the switch? Of course not, because when you open the switch, what is the voltage here? I don't know. This is a floating input. It is floating input. I don't know what is the voltage. So the question is how to hold or store this value when after I open the switch. So I close the switch to take the sample, then I need to open the switch in order to store the value. But if I open the switch, I will lose the value. How can I store this voltage?
Capacitor?
Exactly. This is an analog voltage, and one way to store voltage, analog value, is to use a capacitor. So if I put a capacitor here, then when I close the switch, the voltage on the capacitor ideally also, keep in mind it is ideally, the voltage in the capacitor will be ideally the voltage of this point at the moment I closed the switch. Now, if I open the switch immediately, then the voltage in zero time, the voltage on this capacitor will be 3 volt. Right? So this is the idea. You sample by closing the switch, then you open the switch in order to prevent the input to the A to D to be time varying. You want to have the sample stable and fixed during the conversion process in order to have accurate representation in the digital domain. Okay, so if I just draw what I did. This is let's say the input signal, this is time. So at this moment, let's assume I closed the switch. In other words, I started to acquire or to sample the input signal. Ideally, I will open the switch in zero time, and in this case, the voltage that the A to D will see is this. 3 volts. As the time goes on, it will be held here. So if I close and open in 0 time, ideally I will have this. So if I assume this is the conversion time, this is the time that the A2D requires to convert the 3 volt into digital format, then at this moment I can open, close the switch and open. So I will take this sample, this time, and so on. So this is the time that I need to do the conversion. I can't take another sample before I finish the previous sample. However, this is the ideal case in which I am opening and closing the sampling switch in 0 time, assuming that the capacitor can handle this. In other words, the capacitor can change its voltage to the sample voltage in 0 time. Okay, however, is this the case? Can the capacitor change its voltage in 0 time? Of course not, right? The capacitor and the voltage cannot change in 0 time. So what is going to happen actually if we have I will just draw the actual case. At this moment, I close the switch. So I started to take the sample. Now, if I draw the capacitor voltage, if I assume that VC, this is VC. VC is 0 before I close the switch. And I closed the switch at this moment. Now, when I close the switch at this moment, the capacitor will start to charge. In other words, its voltage will not be 3 volt in 0 time. So the capacitor will start to charge like this, right? The capacitor will start to charge like this. So now the question, when to open the switch? If I open the switch in 0 time, then the capacitor voltage will be 0 volt, right? If I open it here, then the capacitor voltage will be this. If I open it here, then the capacitor voltage will be very close to the sample value. If I open it here, then the capacitor voltage will be this. So if I open the switch here, the capacitor voltage will be very close or similar to the input sample voltage. So at this moment, I open the switch. I can't open the switch in 0 time, because if I do that, the capacitor will not have time to charge or discharge in order to follow the input signal. And probably you know this from RC circuits, right? From RC circuit. So in other words, I cannot close and open the switch in 0 time. I need to wait this time, which we call the acquisition time. This is the acquisition time. This is the time that we need to wait in order for the capacitor to charge or discharge, depending whether the voltage in the capacitor is higher or lower than the input voltage of the sample. Okay, now if you open the switch too soon, then the sample, the voltage of the collected sample will be much less than the actual sample. For example, if you open it here, so you don't give sufficient time, then there will be this, you will have this error between the actual value and the sampled value. If you open it here, it will be very close or almost the same. But practically, if you want this value to be 100% as this, you need to wait for infinity, right? You need to wait for infinity, because the voltage in the capacitor will not reach this unless t goes to infinity. So this is very important. And this block, which is the switch and the capacitor, is basically what is inside the sample and hold circuit, the sample and hold circuit. This is not a mechanical switch. This is an electronic switch in which you can control, as we see here on the slide. Here we have an input signal to the sample and hold circuit, which is basically an input signal that controls this digital switch, and to open or to close the switch, which forces the switch to close or to open. So we don't want to go into more details than this, but we need to be aware that in order to go from here, which is the analog representation of the signal, to here, which is the digital representation of the signal, we need two times. We need the time that is required by the converter to convert the collected sample, which is the conversion time. And we need to wait for the acquisition time in order to allow the capacitor to follow the input signal, to be close to the input signal. The faster or the shorter this time, the larger the error that you will have in the acquisition. Okay, the longer the time, the less the error. However, what is the effect of increasing or decreasing this time?
The voltage magnitude.
What is the total time that we'll need in order, as we said, to go from here to here? It is T acquisition plus T conversion. So the converter needs some time to take this 3 volt and convert it to digital. And also we need to wait for some time, suitable, appropriate time, in order to acquire the sample. So this is the total time before which we can take another sample. Okay, so what does this time represent essentially? It is TS. It is the sampling period, because you need acquisition time, you need conversion time. So this is the time for one sample. Then you can repeat, take another sample. So this is TS. And if this is TS, then this is essentially 1 over Fs, right? So this is the sampling frequency of your system. This is the sampling period of your system, or in other words, it is the sampling frequency of your system. So if you increase the acquisition time in order to reduce the error between the sample and the actual value, you will end up with a lower frequency, right? If you increase the acquisition. What is the effect of having a lower frequency? If your sampling frequency is reduced, what is the effect of this in your system? Yes.
Accuracy.
Accuracy. Basel.
تمام. higher quantization.
Higher quantization. Quantization error has nothing to do here, because quantization is only function of the number of bits.
دكتور انت قصدك اذا قللنا التي اس كامل؟
إذا أنا بدي أقلل الإيرور، خليني أسميه هذا الأكوزيشن إيرور. This is the acquisition error. And in order to reduce the acquisition error, I need to wait longer time by increasing the acquisition time. If I increase the acquisition time, then I will increase the sampling period. In other words, I will reduce the sampling frequency.
مش راح اخذ بوينت كثير بحيث اني راح ابعد عن يمكن الاوريجينال سيجنال.
اوكي، يعني جواب لازم اكثر.
لازم اخذ بوينتس اكثر عشان انا احقق انه فعليا السيجنال اللي دخلت تقريبا نفس اللي طلعت.
Exactly. يعني we just said before that the maximum frequency content of the signal should be less than or equal half the sampling frequency, right? So if you reduce this, the sampling frequency, what does this imply? This implies that the maximum frequency in your input signal will be also lower, will be reduced. So your system will not be able to work with signals that have higher frequency content. Okay, so this is very important. So how to determine the sampling frequency of your system? You need to determine the acquisition time, the conversion time, which is basically the sampling period, and it is the reciprocal of the sampling frequency. So this is a trade-off. If you want to reduce this error, I will call the acquisition acquisition. This is the acquisition error, which is different than the quantization error. The quantization error is related to the way we quantize the signal. Here, the error is related how soon we open the switch, the sampling switch. If we open it too soon, then there will be a big difference between the acquired sample and the actual value. If we wait longer, then the acquired sample will be closer to the actual value. And we will see how this is implemented in our microcontroller, how we can control the acquisition time in the HCS12 microcontroller. Okay. So these are basically the components that you might need in a data acquisition system that is capable of acquiring a signal and convert it into digital format. So as soon as you open the switch, you can instruct or ask the A2D to start the conversion, as we said, through the digital interface that comes with the A2D. So on the following slides, as we said, in the following slides, there are more details on this, on these issues. Here, it talks about the amplification or preconditioning block. And as we said, we might need scaling circuit or translation circuit. And I will leave these to you, how to design a scaling circuit using op-amp, how to design, and this is an example, and how to design a translation, voltage translation or level shifting circuit using op-amps. Okay, so please look at them in order to see, and this is straightforward. I believe most of you took it in circuits or in electronics. Okay, so this is how you can design a preconditioning circuit or scaling and shifting circuit. And there is an example. Also, the filtering, we talked about it. Why do we need filtering? The analog multiplexer and the sample and hold circuit. The sample and hold circuit, which is almost, we discussed it in detail. So you see here, at this moment, we close the switch. So the voltage on the capacitor will start to follow the signal, will attempt to follow the signal. So if we keep the switch closed, you see that the voltage on the capacitor will start to follow the signal. At this moment, we opened the switch, so we enter the hold state. So we hold the sample, and at this moment, we assume that the voltage on the capacitor will stay constant. For example, in our case, 3 volt. However, in practical cases, when we open the switch, this capacitor, along with the internal resistance of the A2D, will form an RC circuit and will start to discharge into this resistor. And that's why here, if you look carefully, here, there is the voltage of the capacitor starts to drop, which they call the voltage drop. So if your converter is slow, then there will be an increased error in the converted value due to this drop on the capacitor voltage. Because practically there will be an equivalent resistance for the A2D, and the capacitor will start to discharge in the A2D as soon as you open the sampling switch. Okay?
دكتور بصير سؤال.
تفضل.
هسه التايم اكوزيشن يعني بنقدر نقول بصيغه اخرى هو نفسه التايم كونستنت تاع الكاباسيتور؟
هلا الاكوزيشن تايم هو مش نفسه، لا. It has to be related. If you want to have less error in the acquired sample, then your acquisition time should be related to the time constant of the RC circuit. And if you remember from the circuits or physics courses, we can safely assume that the capacitor voltage is the same as the input signal, or the transient. In other words, the transient period, the transient time is over if we wait for what? 5 to 7 tau, right? Something like this.
بالضبط.
We wait for, so if you make your acquisition time, let's say 5 tau, which is the capacitor multiplied by the equivalent resistance that the capacitor see when you close the switch, which is the resistance of the sensor in parallel with the resistance of the A to D, then this is the time constant. So if you want to have the least error, then you need to wait for at least 5 tau, which is C times R equivalent, the equivalent that the capacitor says. Okay? So this is all about the data acquisition system. Usually for the undergraduate course, we do some calculations actually here, but we don't want to do it in this case. As I said last time, the analog to digital conversion operation can be implemented in different techniques. So some of these techniques is called the dual RAM, which basically, these techniques, they basically implement some algorithm that attempts to find the digital equivalent of the analog sample. So one technique is the dual RAM, another one is the flash technique, and the other one is the successive approximation. And each of these techniques has its advantages and disadvantages. For example, the dual RAM technique is slow but has higher accuracy. The flash converter, from its name, it's flash, which means it is fast. Usually it is fast, but it has lower accuracy. Usually it is used with high-speed signals. It is fast, which means it can run at high sampling frequencies, which means you can use to sample frequent signals with high frequency content or high-speed signals. High-speed signals imply that these signals have high frequency content. So because they are fast, these converters are fast. In other words, their sampling frequency can be high. They can be used with signals with high frequency content. Another technique is the successive approximation, which is a trade-off, which presents a trade-off between speed and accuracy. And usually this technique is very common when it comes to the ATDs that you find inside microcontrollers, because they are of medium, of reasonable speed, and of acceptable accuracy. Okay, so this is in general the whole idea, and a very gentle and simple introduction to the analog to digital conversion and some of the stuff related to the A to D converters, analog to digital converters. Now, let's look at how these things are implemented in the analog to digital converter that is available in the HCS12. Basically, the HCS12 microcontrollers may have 1 or 2 A2Ds. So some of the models have 1 analog to digital converter, others they have 2 A2Ds, like the one that we have on the board. It has 2 analog to digital converter, A2D1 and A2D0, A2D0 and A2D1. And these A2D converters are 10 bits. In other words, they use 10 bits to represent the result, but you can configure them to operate in 8-bit mode. In other words, to use 8 bits instead of 10 bits. And they have 8 channels, each of which has 8 channels. And what do we mean by channel? Basically, we mean inputs. We mean the size of the analog multiplexer that comes with this analog to digital converter. So each of these A to D can be connected to 8 different sources, can be shared with 8 different sources.
يعني
Now,
الماكس يكون في 8 switches.
الماx, yes, it has 8 inputs. This max, yeah, this max has 8 inputs, and each of them is called a channel or input. The technical name is channel. So here we have four channels. Okay, so I just remembered something here. Now, for most A to Ds that you find inside microcontrollers or that you buy commercially, usually you don't have to bring a multiplexer. You don't have to build your sampling and hold circuit. Usually these 3 components are packaged in one package. So when you buy an A to D converter chip, then you will have inside it the sample and hold circuit and the analog multiplexer. The same case for the A to Ds that are inside the microcontroller. They already have the sample and hold circuit and the analog multiplexers. Okay, so let's go back to the A to Ds inside the HCS12 microcontrollers. Another thing is the highest frequency of the conversion clock is 2 megahertz. So most or all A to Ds, they require a clock to operate in order to do the conversion because all the algorithms, all the conversion algorithms are sequential. In other words, they go into steps. So in order to synchronize these steps and to go through these steps, you need some timing, so you need a clock. So all A to Ds, they require a clock. The conversion process is sequential, so you need a clock in order to time each step. And in our case here, the clock for the A to D inside these microcontrollers has a maximum clock frequency of 2 megahertz, okay? Despite the fact that our microcontroller can take a clock up to 32 megahertz, but the A to D itself, or the A to D module itself, only work with 2 megahertz. Okay, what is here is basically some of the features and associated with the A to D converters inside this microcontroller. And in the following slide, we have a better list for these features. As we said, it can be operated as 8-bit or 10-bit mode or resolution. It has a sample buffer amplifier. It has a programmable sample time. Here they call it sample time, but which is the same as the acquisition time. So the acquisition time is programmable. You can program it. You can specify how long is the acquisition time in your program by writing special values to special registers. The result that you get, which is either 8-bit or 10-bit, can be, as we see, I will see later, can be write justified, can be specified as signed or unsigned. The start of the conversion, in order to tell the A to D to start conversion, you can do that either by writing special instructions, as we will see, or by using some external trigger. In other words, you use some external input to start the A to D conversion process. And that is what meant here by external trigger control. We will talk about it later. There is an interrupt event that is associated with this, with these A to Ds, which is the conversion complete event. You can enable the A to D to interrupt the CPU as soon as it finishes the A to D conversion process. It has an analog multiplexer of 8 channels. The pins that are used with the A to D can be used for digital input. In other words, a general input output. We can, as we will see, specify 1 to 8 conversion sequence length. we can tell the A to D we want to do 4 consecutive conversions or 8 consecutive conversions from the same channel or from multiple channels. So this is called the sequence length. We can configure the A to D such that whenever we tell the A to D perform a start conversion, we can configure it to perform 1 conversion, 2 conversions, 3 conversions in one command or in one instruction, which is the sequence length. We can specify how many conversions to do, whether the conversions are from the same channel or the conversions are from different channel. We can configure the A to D to run in continuous conversion mode. In other words, as soon as it finishes the current conversion sequence, it can repeat it over and over, and this is called the continuous conversion mode or the scan mode. It continuously do the convergence. However, if you don't run in this mode, once the A to D finishes the current conversion sequence, it stops conversion. It will not do any further convergence. And this is what I just said. We can scan from one channel or we can scan from multiple channels. This is a simple block diagram for this A to D module. And as I said, in our microcontroller, we have 2 of these A to Ds. So we have 2 analog to digital converter, and they are identical. They are exactly the same in terms of operation and in terms of internal structure. So if we look at this block, it has certain number of inputs. The first inputs are the V reference high and the V reference low inputs, which are basically pins in the microcontroller. If you go to the pin out of the microcontroller, these are pins through which you can feed voltages to be used by the A to D as the reference voltages. Also, there are 2 other inputs, which are VDD and VSSAA, and A here is for analog. So these are the supply voltages for the A to D, and they are given directly to the A to D in order to run, to operate the A to D. These are different from the reference voltages. So you may have reference voltages from 0 to 3, but the A to D has to be operated by, let's say, 5 volts. And that, why do we have separate input power supply pins for the A to D? Because it is an analog device and it is very sensitive to changes in the supply voltage. Its operation is very sensitive, because if you look, if this is the microcontroller and this is your A to D, usually if you look back at the pin diagram of the microcontroller, there is a pin called VDD, and this is usually drawn like this to indicate that this is a pin, and this is an external pin, and this is VSS. Why not to take these voltages to run, to operate the A to D, and instead we use VDDA, VSSA pins, as I said, in order to have a clean, because if I want to take these voltages and use them for the A to D, these might be corrupted by the heavy switching that is going inside the microcontroller when the digital values are moved around. So this might be corrupted with noise. So in order to have a clean power supply to the A to D, we usually use these. In addition, we have the reference voltages, the V reference high and V reference low voltages. So these are external pins. Other external pins, of course, that you should have are the pins for the channels, So it is an 8 channel pin. So we have 8 pins that are associated or connected to this A to D module. And if we are talking about A to D 0 module, the A to D module number 0, then we have 8 channels, analog channel 0 up to analog channel 7. And these are not only dedicated for the A to D, they are multiplexed. In other words, they can be used for general digital input and output, PAD0, PAD1, 7, sorry. So you can use them for the analog, or you can use them for general input output. And in case you use them for general input output, you need some data register to store the value that you read from these pins, which is shown here. This is port AD data register. In case you use these pins for digital input, in other words, use them as an input port. محمد.
دكتور هسه الفي دي دي اي والثاني هاي هم مش الفي اس اس اي، مش هذول ريبريزنت الانالوج سيجنال اللي داخله على الاي تو دي كونفرتر؟
يس.
اللي هم في كي صح؟
exactly.
طيب هسه خلينا نفرض مثلا انه انا السيجنال الهاير واللور رينج اللي عندي من 0 ل 8، والانالوج سيجنال اللي داخل الانبوت مثلا من 1 ل 3، مش هي نعملها سكيلينج باي الامبليفاير؟
Yes, so you connect your amplifiers here.
تمام. هسه الامبليفاير يحقق المعادله اللي احنا اخذناها اللي هي في كي ايكوال ناسي كم، بس يحققها يعني.
Amplifier has nothing to do with that equation. That equation relates the digital output with the input sample value.
تمام.
Okay, so in order to know the actual sample value before scaling, you have to do reverse calculations in order to get by reversing the equation of the scaling circuit or the translation circuit. Okay.
يعني for one sample صح؟
Yes, for one sample.
تمام.
Okay.
Thank you دكتور.
Okay.
تمام.
دكتور عندي سؤال بس.
Yes, باسل.
دكتور هلا المالتيبلكسنج والسامبلينج ريت، هلا لما نعمل مالتيبلكسنج اكيد السامبلينج ريت لكل انبوت راح يقل، مظبوط؟
اكيد.
لانه لو عندنا سيجنال واحده فهذا الاشي نتحكم فيه احنا بهاي المايكرو كنترولر، ولا هو ثابت لكل واحد؟
لا.
يعني لو
صوتك بس بيقطع هو باسل.
اوكي. اللي سؤالي، سامعني دكتور؟
سامعك انا.
سؤالي لو شبكت انبوتس اكثر يعني انالوج اكثر راح يقل عندي السامبلينج ريت لكل وحده؟ مش هيك؟
Yes, منطقيا yes. Imagine like this. At this moment, imagine that you are using two channels on. Let's first take one channel. You are taking samples from one channel. So you have some acquisition time, then you have some conversion time. So this is for sample 1 from channel 1. Okay, this is sample 1 from channel 1. There's a problem with the video. Then you can take sample 2 from channel 1. So basically this is your sampling period, right? This is your sampling period, and accordingly you know your sampling frequency. However, there's a problem with the software that I'm using, I guess, to take the image, to take the video. However, if you use two channels, so you are sharing the ATD between two channels. So you need some time to take the first sample from the first channel. Then you need some time to take sample 1 from channel 2. Then you take sample 2 from channel 1. So effectively for channel 1, what is the sampling frequency? Is it this, or sampling period? Is it this, or is it this? It is this, right? So of course, if you increase the number of channels that you are reading from, then your effective sampling period will be n times the sampling period for one channel. So the sampling frequency will be scaled down by n. Okay.
تمام. وفي شيء بيتحكم فيه بالهاي المايكرو كنترولر، يعني ممكن احكي له كم شانل بدي؟
Of course, yes.
تمام.
محمد have a question.
دكتور هذا من قبل سوري بدي اعمل انرايز سوري.
Okay, تمام. All right. So here we have the channels. Here we have the channels that we can pick from. In order to do the sampling, we can take the sample from 1 channel, 2 channels, 5 channels, 7 channels. We can do the conversion to be continuous. We can do the conversion 1 time. We can take 5 samples, 10, 6 samples, 1 sample from 1 channel. We can do all these configurations. We can configure the ATD to run in any of these modes. Then we have here the sample and hold circuit, as we said. And we have the hardware that implements the successive approximation algorithm in order to do the A to D process, and the result is stored in a special function registers called the Atd registers, and these are ATD0 up to ATD7. So we have 8 registers in which we can store the result, whether it is 10-bit or it is 8-bit, and each of these registers essentially is 16 bits in order to store 10-bit value. Also, another input is the clock, which is driven from the bus clock, and as we said, the clock that essentially goes to here has to be maximum 2 megahertz. It has to be no more than 2 megahertz. So there is some scaling that we can control. In order to scale the bus clock, we need to do some scaling, and this is configurable. You can change by changing the value in some special function registers that are associated with this ATD. Okay, so this is the general overview of the inputs of this A to D and where the results are stored. And once the conversion is complete, there is one output associated with this module, which is the conversion complete interrupt, which can be configured to interrupt a microcontroller once the conversion is complete. One more thing here, as we said, these pins can be used for general input-output. For example, you might not need to use the A to D in your system. And that's why by default, the A to Ds in microcontrollers, they are disabled. They are poured off because they consume a lot of power. So if you want to use these pins as inputs, you need to come to this register, which is called the A to D input enable register, as we will see, in order to configure these pins as digital input and read the value into this register and use it, in case you don't want to use the A to D. So also these are also, I kind of talked about them here. It tells us that the microcontroller that we have, it has 2 modules, AD0 and AD1. This one is associated with analog input 0 through analog input 7, while this one is associated with pins analog 8 through analog 15. And these can be seen on the data sheet. As we said, these are the reference voltages, and these are the supply voltages. One more thing related to these pins is AN7 and AN15. Now, there is a problem with this thing. It keeps stopping this program. This pin, AN7, can be used as an external trigger, and AN15 can be used as the external trigger for the A to D1 module. And what do we mean by external trigger? As I said, you can configure the A to D to start the conversion, for example, when it sees a rising edge on AN7, or when it sees a falling edge on AN7, or when it sees a low level or a high level on AN7. This is useful to synchronize the operation of the ATD with some external event. For example, you can connect a switch to this pin and configure the ATD such that whenever you press the switch, a conversion starts to read some analog input to convert it from some other channel, not from this channel. You can configure, for example, you connect this to some sensor such that whenever somebody passes it through, you start the conversion process from some other channel. So this is what is meant by external trigger input.
دكتور بس آسف، بس بصير تعيد أول بداية الشرح اللي كنت تحكي عن التريجرينج لأنه شوي الصوت قطع عندي.
Okay, as we said, this pin can be used to input any analog signal to be converted, or it can be used for digital purposes, or it can be used as an external trigger to control when the ATD starts the conversion process. For example, you can configure this pin and the ATD such that whenever there is a rising edge, the ATD will collect a sample, let's say from channel 0, and convert it. Whenever there is a low level or a high level, this will be like a stimulus or a trigger to the ATD to start the conversion process. Okay? Okay. So now, similar to all peripheral devices, similar to all features of any microcontroller, in order to control this ATD, we have a set of special function registers that can be that you need to work with in order to configure and operate this ATD. And this list of registers is given here. We have 6 control registers, which are A to D 0 up to A to D control 5. And X here is either 0 or 1 to refer to the registers related to ATD 0 modules or ATD 1 module, and which are identical in operation. Okay, so 0 or 1, X is basically 0 or 1 to refer to one of the ATD modules. So these are the control registers through which we can specify what is the acquisition time. We can specify which channel we want to take samples from, through which we can specify how many samples we want to take per conversion, and all that stuff that we mentioned earlier. There are 2 status registers, which are called status 0 and status 1 register. And they have some bits to indicate or to express something, to indicate some status related to the ATD itself, and 2 testing registers, test 0 and test 1, which can be used to test whether the ATD is operating properly or not. And as we said, there is 1 register that has to be used when we want to use the analog pins as digital inputs, which is the A2D digital enable register. And basically this register, you store in every bit, you store either 0 or 1 to indicate whether it is used as a digital input or a digital output, or an analog input, I'm sorry. There is 1 port data register in case, as we said, you use these pins as digital inputs. The digital value is stored in these registers. And finally, we have 8 result data registers, which are A to D data result 0 through 7. However, we need to keep in mind that each of these registers is 16 bits in order to be able to hold the 10-bit result in case we use the A to D in 10-bit mode. All right, so next time we'll look at these registers, how to use them to configure and use the A to D. But in order to save some time, please help me by going through these registers. They are very simple. If we understood the idea that we have an A to D with the channels, with a clock, we can pick the channel to take the sample from and convert. And this, our pick can be from multiple channels, can be over rounds or over sequences and all that stuff. This can be controlled using the control registers from 2 up to 5. Control registers 0 and 1 are only used for factory testing. So we will talk about control register number 2, 3, 4, and 5 only. Okay, then we will look at examples. Now, there are many slides left, but we already discussed some of the stuff that is present on these slides. So next time we'll go through these and look at some examples, how to use this ATD. Now, I know when we present such topics, it is very important that you do some practical work. But however, we cannot do it at the moment. But what I'm thinking of is basically some of the homeworks. Let's say today you were supposed to submit homework number 2, right? I will leave at least one homework. I will delay it as much as I can, such that you will be able, hopefully, to do something with the board. I will not ask you to do the project, as we said last time, unless you want to do that. But if we are able to go back, let's say by the beginning of May, then I will try to give you the boards so that you do some practical work with it in order to have some sense of what's going on. For example, to use the ATD to acquire some value and show it and all that stuff. However, for the time being, we don't have any choice. We have to go through them in the way that we are doing. But I think it should be fine. All right. So on Monday, I will do my best to finish this chapter. We don't have much left, the registers and the slides.
الله يعطيك الف عافيه دكتور.
الله يعافيكم يا رب. فالجميع سلم الهومورك. Everybody submitted the homework. I did not check actually the e-learning. If you submitted your homework through e-learning, please raise your hand. Raise your hand if you were able to submit your homework through e-learning. Okay, Basil. Yes, you did. Okay, great. So next week we'll have quiz number 3, right? On Wednesday we said, and it will be about chapter 4 and chapter 5, right? Chapter
بس
4.
دكتور والله اذا سمحت يكون اخف من الاول، لانه الاول كنا مصدومين واول مره، والوقت صراحه كونه اول فرع كان فيه شويه خربطه في الدايركتيفز، وعن جد هو يعني اخذ مني كثير وقت وراح علي الباقي يعني انا جبت 2.
ما في مشكله، ان شاء الله بنشوف ان
شاء الله دكتور،
ان شاء الله. يلا اوكي،
الله يقويك.
يعطيك العافيه.